Okay, so I just want to talk a little bit about the solution. So the solution rho of xt, is rho of xt is going to be 1 when x is less than t, 2 when x is greater than t, and x over t otherwise. And I just want to sketch a few of the solution curves just to give an idea of how this evolves as time goes on. So this is going to be the x-axis, and this is the rho axis. And this first picture is going to be what happens when t is equal to 0. So this is the initial rho. And rho is going to be 1 when x is less than 0. And it's going to be 2 when x is greater than 0. Okay, because there t is equal to 0. Okay, now let's look to see what happens maybe when t is equal to 1. Okay, so this is going to be when t is equal to 1. So again, this is the x-axis. This is the rho axis. This is going to be what happens when t is equal to 1. Okay, so what's going to happen if I look at my solution for rho, when x is less than t. In other words, when x is less than 1. When x is less than 1, the solution is going to be equal to 1. But now when x is greater than 2, so it goes off that way. When x is greater than 2, the solution is going to be 2. So it'll be something like this. And then it's just going to be the linear interpolation between those 2 points. When x is in between, this is x is equal to 1, this is x is equal to 2, and in between it is going to be the linear interpolation. Okay, let me draw a couple more. Let's look to see what happens, let's say, when t is equal to 3. Okay, so when t is equal to 3, let's say this is x is equal to 3. Okay, so it's going to be 1 when x is less than 3. And then if I come up here, it's going to be equal to 2 when x is greater than 2t. So it's going to be, let's say this is 6, that's 2t. It's going to be 2 from this point on. And it's going to be just the linear interpolation between those two. Okay, so what happens is we can see that as time goes on, we're going to get this expansion. Again, it's called an expansion wave, and the distance between, so like the whole like rho profile is moving. Okay, but the distance between the rho equals 1 and the rho equals 2 is expanding, and so that part's kind of, again, that part is expanding. This also, we'll say more about why we pick this solution, but the idea is that, if I look at a very small value of t, like let's say I look at t is equal to epsilon, a very small value of t. T is equal to epsilon. So this is epsilon, and so I don't know why I keep doing that or how I keep doing that. So if I look from x going from x being less than epsilon, we're going to have something like this. And then very close to it is going to be 2 epsilon. It's going to be 1, and they're going to have this very sharp linear function going from between those 2 points. Well, if we kind of trace this back, this profile back as epsilon goes to 0, as the time goes to 0, this becomes a horizontal line. And so the idea is that kind of instantaneously, all of the characteristics are sort of present instantaneously when t is equal to 0. And that's what happens. That's one of the motivations for kind of doing this thing right here, where we're really just looking at all of the different characteristics that could possibly exist in this wedge. Now, that's one reason that we've picked this solution as the sort of main solution, the physically reasonable solution. Again, like I say, once we look at shocks a little bit in a couple of videos, we'll be able to give another physical interpretation for why this is the solution that we're calling the main solution. Because like I said, there's not a unique solution to this problem, but the method that we've described here, this is the method that we're going to use to find a solution, and this is the only physical reasonable solution.